In Part 4, System Design Options and Considerations, we'll look at the integration of heat pumps into the overall heating system for a home. Our learning outcomes for Part 4 are to understand the different air source heat pump designs and their intentions, to learn the different design options for air source heat pumps by home need, and to understand key considerations for system design.
Let's continue with Part 4. Part 4 deals with the integration of the heat pump into the overall heating system for the home. The approach to system design falls into two major categories: whether to replace the existing system entirely with a heat pump system, or to replace only a portion of the existing heating system with the heat pump. Pictured on the left, the bottom floor of a two-story home, colored in gold, is to be heated with a heat pump, while leaving the top floor, colored in blue, with a legacy or existing heating system. This intended design is commonly referred to as a displacement design, where the heating load is partially served by the new heat pump, displacing a portion of the home's total heating load. Pictured on the right, where the entire conditioned space, colored in gold, is to be served by the heat pump system. This type of intended design is referred to as a replacement system. This graph shows a scenario where a heat pump is sized and selected to meet the heating load about 91% of the time. Along the horizontal axis on the bottom are the outside air temperatures shown along here, varying from 50 degrees outside down to 5 degrees, which is the design temperature. At the design temperature, the home's heating load is 48,000 BTUs an hour, shown here. The blue line indicates, as we've said before, is the actual heat load on the home. This orange line represents the maximum capacity of the heat pump. And then along the right-hand vertical axis here, we have bin hours. That is the number of hours at a particular temperature, outside air temperature. So for instance, at 50 degrees, there's probably somewhere around 180 heating hours a year at that temperature. And then as we go over to the left, you can see at 45 degrees, it's somewhat less. And down at 30 degrees, it's like 225 hours a year. But then as you move further to the left, you'll see that the number of bin hours becomes less. There, even at these extreme colder temperatures, there are fewer hours during the year that these occur. The pink area is the area of shortfall from this particular heat pump selection. So they've selected a heat pump that can serve 100% of the load at about, it looks like an outside air temperature of somewhere around 18 degrees. And so that is shown here. That's actually the balance point. And then over here on the left, it shows this is the design load of the heat pump. And so the heat pump can furnish at the design temperature 30,000 BTUs an hour of capacity. So it leaves the shortfall, as I said, of about 18,000 BTUs an hour, which has to come from some other place. So the places where this additional supplemental heat can come from could include a legacy system that still has capacity to meet that additional load, or it's actually a partial load if it were a legacy system. It could also come from another heat pump. It could come from, another form of heating, such as electric resistance heating, or it could even come from a hydronic convective system. Now here, we're looking at a situation where how we're going to serve the home. And this is basically in terms of whether you want to use a zoned approach or you want to try to heat the entire home with heat pumps. Could be one or it could be several. But in this case, we're looking at, on the left, the home is split into two zones, or really three zones rather, each having its own heating system. Each zone has its own thermostat and controls, and it's probably better suited in a situation where you have a larger home or where you have a complicated layout. And so on the bottom here, you can see in yellow is the first zone, and that's presumably the downstairs, looks like a living room, maybe dining room combination with a kitchen. And it's being served really with one heat pump. And in zones 2 and 3, these are upstairs. Zone 3 looks to be like a bedroom area, and zone 2 is probably an area of the home that's a little bit further away from everything. See zone 3, how close it is to the stairway. So it's going to get more heat from downstairs, whereas zone 2 is somewhat more isolated. And so meeting those loads can be done in a variety of ways, which we'll talk about. And then on the right, this is a home really where it's all one zone. And this is generally more applicable to homes that are smaller and where you might have an existing ducted system or where you may want to use a ducted system. And also a home that maybe have a relatively simple layout. There's also the option, one of the larger areas of decision here is whether you want to use a ducted system or a ductless system, or, maybe a combination thereof. But we'll talk about just these two to start. In a ducted system, the heat's distributed through each room through ducts, and the heat pump then interfaces with an air handler that is attached to the ducted system. And these are probably best if you're going to have a full replacement system. The ductless systems are more flexible. They can serve individual rooms or groups of rooms or zones, and the heads want to be located in strategic positions. It's best for a displacement type system or a partial load system rather than an entire home. And it's also better suited in cases where you have a simple home layout. So if the home layout if the home is bigger and if the layout is more complex, in general, one would want to lean more towards a ducted system rather than a ductless system. The ductless design options that you have really are individual mini split units, or on the other hand, a multi-split unit. Now, multi-split units, we've said previously that we don't want to really have more than 3 heads attached to one outside unit. But for just purposes of demonstration here, we're showing the various options for the air handlers inside the home. On the top here, you can see this is a representative of a compact ducted system. Below that, on the left, is a wall sconce air handler. On the right, just below the compact ducted system, is a ceiling unit. And then on the bottom below that is a floor-mounted air handler. Here's a situation where you could have a combination. You probably are best having a compact ducted system where you have short runs. And these are short duct runs of 15 feet or less, as opposed to, we're not talking about the refrigerant lines here. We're talking about the ducted system itself. And it's useful usually in situations where you have a cluster of smaller rooms together where they can be served by a mini ducted system. And this will also minimize the pressure and thermal losses within the ducted system. Then looking at a combination here, you could have a compact ducted system that serves part of the load, and then you could have other parts of the load that are served by a couple of mini splits. An example of this would be maybe using it on the first floor. Maybe you have a couple of mini splits in key areas, and then up on the second floor, you might have a compact ducted system. On this slide, we're looking at a home with a relatively simple layout, and we have 2 ways of maybe serving this load. One would be ducted versus having a ductless system. It's a simple single-story home, looks to be about 3 bedrooms, a master bedroom on the lower right, and 2 other bedrooms with a bathroom in between. And then in a large room on the far left, which is probably a combination dining living area, and then a kitchen in the middle on the bottom. On the top here, what we're talking about is serving the load using a ducted system. So here you can see a ducted. This is a large ducted system, and this may very well be a legacy system where you have heat ducts supplying warm air to the large room. Each room here actually has its own supply duct. And you can see that there's heat going in. The heat is being represented by this kind of orangish color, and where it's yellow, there's a little less heat being circulated through the room. What you see here, though, is that each room is receiving some heat. In the ductless system on the bottom, there's only one air handler shown and one outside unit, and that heats the big room. And they're counting really more or less natural convection to carry that heat through to the other rooms. You can see the other rooms are not really getting a lot of heat, but they may not need it so much because most of the rooms on the right-hand side are bedrooms. Under a lot of circumstances, maybe those can be served with the heat available from the large living dining room area. Also, one thing with these, both a ducted and a ductless system, you have to be very choosy about where you select to locate the thermostat. You definitely don't want it on a wall where the sun's going to shine through the window onto the thermostat. That will give the thermostat a false reading. So you want to locate it probably in a hallway where there's no direct sunlight going to it. Some other things you may want to think about in terms of the design of a duct system. First of all, you want to be using manual D, just like you want to use manual J for calculating your heat load. You want to be using manual D to design your ducting system. And you want to assure that you're going to have sufficient airflow through the ducts, and that's a function of its size. And you need to be aware of what the static pressure is going to be, and you want to minimize the pressure drops, so you don't want to have sharp bends. And if you do, you want to use turning vanes, and even in your return ducting, you want to use vanes if you have sharp bends. You want to place the ducts in conditioned space whenever possible. That's always better than having it in a cold basement or a cold attic, if you have the space available. The air seals for the ducts, you want to use mastic or aluminum tape, or you can use the two combined. You do not want to use duct tape, even though they call it duct tape. It's not really designed for duct work, and it will dry out quickly, and then you're going to have a leaky duct. And for some ducting, gaskets are available, and they're good to use if the system allows. In all cases, you do want to test for leakage. You don't have to put a lot of pressure on the ducting, but you should positively seal it off and put a pound or two of pressure on it and see if it holds the pressure for 15 or 20 minutes. You want to insulate all the ducts in the unconditioned space, in addition to the conditioned space, whenever possible. And you really want to insulate to an R value of at least 8. The ductwork, if it's going in a floor joist, you want to probably bury it in insulation if you can, and as deeply as possible. And it's, as I said, it's always a best practice to insulate all the ducts, even if they're in a conditioned space. Now, in locating your outside unit, there's a few considerations that have to be taken into account. Number one is snow. Now, you'll see pictured on the upper right an outside unit that's on a little stand. Presumably, you want to locate the outside unit above the normal maximum snowfall level. That way, your outside unit, when it's cold outside, you have to be able to extract heat from the outside air. And the only way to do that is to circulate air through the outside unit. So if it's covered with snow and the air can't pass through the outside unit, you won't get any heating at all if it stops the flow of air. And then you may want to locate it on the gable ends of the house. Typically, those have a little more overhang sometimes than the other two sides of the roof of the house itself. But if the front and back of the house is, if the gables are on the sides, if the front and the back have a large overhang, it would still be okay to locate it under that. But you do want to provide some type of protection overhead for your outside unit. And, you could consider putting a small little roof over it. The condensate lines, one of the big considerations there is you don't want the condensate to freeze when it's cold outside. Because if the condensate freezes, that's going to be a mess. It could crack the condensate drain piping. It may, if the condensate drain goes on to, say, a walkway, sometimes they stack these outside air units one on top of another. And that's probably not a good practice unless you're very sure that you have a good condensate drainage system. As far as the line sets are concerned, part of this is going to be a function of how big the house is and what your overall strategy is for servicing the heating loads. But the line sets in general want to be kept to a minimum. So you want to consult with the manufacturer about their particular unit and what the maximum line sets are and what the diameters should be. Common diameters of HVAC tubing is 1/4 inch, 3/8, and a half for a large portion of these types of units. If you have additional line set length, then you're going to have to add additional refrigerant. And so the manufacturer will help you with the correct amount of refrigerant you should have charged to the system. Again, here in all cases, you do want it kept as short as possible. Ideally, it should be less than 25 feet in length. Noise and vibration is also a concern, and locating this outside unit adjacent to a neighbor's bedroom window, let's say, is probably something that you want to avoid. And vibration can be an issue, and if it is, you want to address it. It could be that you're not on a firm ground. And then also there's an issue of animal protection. You can have a raccoon or a squirrel or something chew into the insulation, and otherwise, I don't think they're going to attack the copper tubing, but they could definitely be a problem in terms of your control wiring outside. Big picture consideration is whether you want to have the legacy system continue, let's say, as a backup or a source of supplemental heat for the home. In a backup situation, it's going to be capable of serving the entire load of the home if need be because of a problem with the heat pump. It's critical, though, to make some arrangements to prevent freezing of water lines. And a possible solution there could be something like electric heat tracing of the line. The backup system can be gas, or it can be oil, or it could be electric resistance heat. The backup system, though, is intended to only run infrequently. And if you do have a backup system, it's necessary that the thermostat and the controls are integrated such that the backup system doesn't run when it's not supposed to. Supplemental heat will only cover a portion of the home not served by the heat pumps. So that's intended to run more frequently than the backup, that is. And the thermostat locations and the settings, again, must be integrated. The heat pump has to work in a coordinated fashion with the backup supplemental heat. Some design considerations to discuss with your customers: their willingness to do load reduction measures first. And that's key because, as you know, you can have a home that's poorly insulated or poorly sealed, and addressing those issues first can change the load calculation and the size of the unit. If the customer has a desire to reduce or eliminate the use of fossil fuels because of global warming, then that's a motivating factor. And occupancy patterns are important to identify, whether they go away for a long period of time, let's say in the summer or in the winter. Many people in a cold climate will, particularly retired people, will tend to go south for the winter. And do they want cooling throughout the entire house or maybe just a portion of the house? Cooling in general is in a two-story home, or sometimes if you have a lower level of the home that's partially underground, that area may not need so much cooling because it may not get direct sunlight, and it also, walls will be underground where the temperature year-round is somewhat lower. So they may only want to, or only need to, really cool portions of the home. And then cost, always a major factor. Here, you're probably going to do your customers a favor by having them get an efficient unit that will pay for itself over time, so-called life cycle costing, versus simply the front end or first cost of the unit. And then lastly, you want to find out from the customer, do they have plans for renovating the home or any additions that they might add to the home? And then build that into your design for the house in light of those things as a possibility. And then in this drawing, we're showing an existing forced air duct system. And the supply lines are shown and indicated in red, and the return ducting is shown in green. And what you'll notice is that it has at least one, in the case of the kitchen and dining room, this is kind of an open concept here between the kitchen and the dining and the living area. They're really showing two supply registers in that room. Then they're showing heat supply really to almost every room of the house, not the storage area, but certainly the vast majority of the home is covered with supply ducts and return ducts, which is somewhat unusual, but very good to have because you get much better airflow through the house with a system like this. So one of the things you want to consider is, does the house already have ducts? And can they be either repurposed in part or replaced, but modified in some way, or maybe even used as is? Is the home's current heating system already zoned? What's the age of the system and how long is it predicted to last? Does the home have electric resistance heat anywhere in the home? Does the home's layout include multiple floors or isolated wings? Is the home's main living area open concept, like is shown here, for free movement of conditioned air? And are there constraints on where to place the outdoor air units, such as a close neighbor? Is there sufficient space and power capacity in the breaker panel? Now, if the home already has an air conditioning system, it's likely that they probably have either a 40 or 60 amp service to the existing air conditioning unit. And in many cases, that can be repurposed to serve the heat pump. And then, are there opportunities for load reductions first? Of course, this is first things first. That should be the consideration before actually designing the system. And that concludes part 4.
In part 4, we saw the difference between displacement, where the heating load is partially served by the new heat pump, or replacement, where the entire conditioned space is served by the heat pump system. With system replacement, we looked at a zonal versus whole home approach. Large homes with more complicated layouts lend themselves to zones, each having their own thermostat, while smaller homes with simpler layouts can use a whole home design with one thermostat. This is also best with a ducted system. We looked at ducted versus ductless systems. Ducted systems are best for replacement designs, whereas ductless systems use individual heat pump heads for distribution. Ductless systems are very flexible and are best for partial load displacement or simple layouts. And a system can be a combination of ductless and ducted. And we saw that careful consideration of duct layout, outdoor unit location, and understanding the homeowner's needs are all key for a successful system design.